Okay, so we started off the beginning of the year using the derivative and talking about the slope. Now we're actually going to switch gears, and this is for the second half of the year, and we are moving into integration. And integration is basically just the area under the curve, but we do need to start with how this was developed and where the foundation of integration comes from, and that is from Georg Riemann and the Riemann sum. So if you were asked to find the area of a figure, you would go back basically to your roots in geometry, and you could find the area of a rectangle, area of a square, triangle, circle, trapezoid, pretty much any geometric figure. The problem here is when you're given a curve that looks like this, and I ask you to find the area given these two boundaries right here from A to B, okay? And I want you to find the area under this curve. This, if I'm not mistaken, is not a geometric shape. At least one that we can identify a true area formula. So what we need to do is figure out a way to find the area, and someone actually did that. So a couple of things that need to occur first is when you are given this function, the function must be continuous. And it says, excuse me, non-negative. And basically what this means right here is your graph is above the x-axis. Okay, and they give you a set interval, okay, because it can't go from negative infinity to positive infinity, then you don't have any endpoints. And they want you to find the area between the graph and basically the x-axis. So this is what we're looking at. So if you weren't in calculus, you'd probably say, well, I don't really care. And some of you, even if you are in calculus, might say you don't care. But you need to care because this is actually what we're going to do. So if we were to take this graph, this shape, and if we were to ask you to find the area under the curve, but if I said, okay, let's use rectangles, we are going to approximate. So if I had a way to find the area under the curve and I knew what this function was, what f of x was, I could get a definitive area. The problem here is we are going to have to use a geometric shape to approximate. So that's the whole idea behind the Riemann sum, is approximation of the area under the curve. So if you notice here, we still have a curve. But what we're doing is we are looking at this area that's underneath this curve of f of x from A to B, but now we're using these rectangles. And what do you notice about the rectangles, or the area of these rectangles, and then the area that would be underneath the curve from A to B? Do you notice anything? Is it solid? Yes, Ben?
There's gaps.
There's gaps, meaning some of these, which I'll show, like this one right here is a little bit under, right? It goes a little bit out, but then this one goes outside the curve. And then there's a hole or a gap here. This is outside, and this is what we're talking about from beginning to end. So we would find the area of this rectangle here, meaning length times width, or height times width, whatever you want to call it, and then this area here, and so on. And then we would add all these together. This would be an approximation. And as Ben pointed out, some of the areas are either under approximating or over approximating. So that's why this is a crude approximation, especially this one. We have 1, 2, 3, 4, 5. So in this case, we are approximating the area using 5 rectangles. Okay, so you can clearly see that there are a lot of gaps. So let's move down here. We double the amount of rectangles, and what do you notice about those gaps? Yeah, there's less. Okay, so we're approximating the area, in this case, using 10 rectangles. And then what do you notice about this one? This is actually approximately 40 rectangles. There's way less gaps, right? I mean, you can barely even see it. There's so many. So the whole idea is to get an infinite number of rectangles to represent the area. The larger the number of rectangles that you have, the more accurate the area under the curve will be. Does that make sense? So if you take a look up here, huge gaps, whether it's an over or under approximation, as you get more rectangles underneath that curve, you have a better approximation of the area. So the area here is approximately 40 rectangles. Okay, this is the whole idea behind the Riemann sum. Okay, so let's jump to page 3. All right, so here we're going to cover a lot of notation and definition type. So I just want everybody to make sure you understand here. So first of all, we have our definition, and we're going to cover the left, right, midpoint, and trapezoidal. And for whatever reason in our book, trapezoidal's in Unit 7, so it's kind of combined already in here. So we do cover a little bit of Unit 7 in this class. I think BC covers all of Unit 7, so that puts you at an advantage where you're not covering as much, or a disadvantage, however you want to see it. Okay, so definition, or the area under the curve. I told you that the function has to be continuous on a closed interval, and the function is greater than or equal to 0, meaning above the x-axis for all x values in that closed interval from a to b. So what we're going to look at is some of this notation here and what it means. And it's important that when you look at this, you understand. So as I indicated before on the previous page, I said that what we're doing right now is we're approximating the area under the curve by finding the area of rectangles and then adding all those areas together. Depending on the number of rectangles, it can either be a very crude approximation or a pretty accurate approximation depending on how many we have. The less we have, the less accurate the area is going to be. Does that make sense? Based on what we saw? Okay, so what we have here, does anyone remember what this symbol means? Yeah, it's a summation. It's the sum, sigma. It's the sum of whatever is to the right of it. So in this case here, we have sigma, for those of us that don't remember. Okay, we have sigma. And then what we're taking a look at, we said we're adding or finding the sum of all the rectangles. And the way we find the area of the rectangle is length times width, or height times width. We're going to say height because our rectangles are going to be standing up off the x-axis times our width. So this is what we have. We have delta x right here, which represents our width, meaning how wide each rectangle is. So this right here is our width. Okay? And then f of x sub x star. What's f of x? Forget about the sub k star. What is f of x? It's our y value. So wouldn't that represent our height? Okay? So this right here represents our height, which is our y value. Okay? So this right here is the area. This x sub k star represents each given value that you're going to plug in to the function to find your y value. Okay, and I'm going to talk about how you would identify those values in a few minutes, but this is just the notation we're finding our x times our y, our width times our height. So this is saying the sum of the given areas of the rectangle, but what we need to know is how many do we have, right? So what we have here is what's known as our lower index, which in plain English just means where we're going to start. Okay? And then what we have up here is our upper index, which is where we're going to end. And this will indicate how many rectangles we're going to have. Okay? More specifically, this portion right here. So we're saying the limit as n, meaning this right here, approaches infinity. Okay. So in the first example, we had 5 rectangles. So we're saying as n approaches 5. Then we had 10. Then we had 40. But remember what we noticed, the more we get, the more accurate our area is going to be. So they're saying as the number of rectangles gets infinitely larger, you're going to have a more accurate area. Now, I'm not going to say, okay, find the sum of 500 rectangles. That's going to take you forever. Okay, so that's eventually when we're going to get into the actual integration. So we want to see what happens if we're using a left and right approximation, how that changes what the area is. And I'm going to show you those examples. So this right here represents the number of rectangles. Okay, so that's what all of this means right here. And what they say in this explanation is that these values, remember I said of x sub k star, so this is x sub 1 star, x sub 2, all the way to the nth value, can be chosen arbitrarily, at random. Okay, so if that is the case, then it's possible that our areas are going to be different. But it actually turns out levels higher than this calculus class, it was proven that that's not going to be the case, because there's actually a pattern and a fashion, a system that you're going to use. So just like if I were to ask you to use the quadratic formula, pretty much everybody knows what it is. So everyone's going to get the same answer provided you know what you're doing. When I show you the methods for the left, right, midpoint, and trapezoidal, the systematic fashion in which you find these values is the same. So everyone's going to get the same answer. So you're not arbitrarily choosing these at random and saying, oh, okay, I'm going to look at rectangles 2 through 7 while Ben's going to look at 1 through 4. Okay, everyone's going to be choosing the same values, so there's a system in which this happens, so you're going to get the same area every single time. Does everyone understand what I'm saying? So you have to make sure you pay attention. It's not a given formula, it's like a system of what you're supposed to do, and I'm going to show you how to do that. Okay, so these sums that we're actually going to be finding are known as the Riemann sum. Okay, and this dude right here, his name is not George, it's Georg. Okay, there's no E on the end. All right, and usually these really smart dudes that figure all this stuff out have unique name, Euclid. I don't really know if I've ever met an individual named Euclid. I'm sure there's one out there somewhere, okay? But these are old school, right? All right, so if you're really interested in what he did and how he figured this stuff out, this is his biography on page 354. Otherwise, I'm going to start talking about these sums here. And it is really important that you guys understand how to identify over and under approximation given a graph. So that's what I'm about to show you. And with the left and right endpoint, we're using increasing and decreasing of a function, whereas midpoint and trapezoidal, you're using a different method. You're using concavity. So it's kind of important that you understand where this stuff comes from. So what we have here for our left and right is the exact same curve. So I'm going to highlight this curve real quick. Okay? And we have the rectangles underneath that are going to help us find the approximate area under the curve using a left endpoint approximation. Okay, so what I have here in pink is my curve. All right, and we're looking at going from some value A to B, and we're using a left endpoint method. So that means technically what we're doing is we're starting on the left. Kind of makes sense, right? And then we're moving to the right. When we do the right endpoint, we're going to start on the right, and we're going to have to actually move left to create these rectangles. So what you do is you would plug in whatever that first point is, whatever A is, and you're going to plug that in and find the Y value. But if your curve is already here, what you would do is you would figure out what this width is, and if you look at these rectangles, it's implied right now, that these are even. I'm going to talk about unequal and equal subintervals, meaning your width is going to be different or the same. In this case, they're all the same. It's going to make it easier for the explanation. So what you would do is go from this first point here, and you would go up to the curve and create a point. So that's your first left endpoint. So let's say that A was 1, and I told you that your width was a value of, let's just make it easy, 1. So if I go from 1 and my width is 1, what's this next value going to be? 2, and then you would be able to mark 2 on the graph and then go from that value all the way up to the curve and create another left endpoint. Does everyone understand what I'm saying? Granted, here this is very general. You don't have a lot of information. So if this is 2, that means I would make it to 3 by the width, because the width is the same, and then I would draw from 3 up to the actual graph and create another point. So does everyone see where these points are coming from? It's to help us create our rectangles to find the approximate area under the curve. Okay, so now what I would have to do is create these rectangles. So I'm starting on the left, and I already have this line going up to create part of my rectangle. So because I'm under the curve, and this is the height of my first rectangle, I need to actually create the rectangle, so I'm just going to draw a perpendicular line that's going to go over and meet the next line, or the next height. So that creates my first rectangle. Okay, so in this case I didn't have to extend anything because the line was already there, the height was already there. For this next one, if I were to do the same thing, you notice there is no, even though it's on your paper, technically there's no height here because the height for the next rectangle ends here. So I would have to extend this one up so that I could create this rectangle. So that might happen, and in this case this would be an over approximation because it goes outside the curve. Does that make sense? Okay, so I'm creating this next rectangle. And you would proceed to do the same thing for the rest of these. Okay, so some of these we had to extend up. This one, you notice here, you do not. You do not have to extend up. And then this one would have to extend up from the very end. So this is how you would create your rectangles. Yes, Ben?
If there's no point at the far right, how do you...
This one?
Yeah.
Okay, so this is your ending value. So this is basically the cutoff, so you would just have to extend that up. Even though there's no point, but then when I go over here to do the right end point, there will be a point. Do you see?
Oh, since it's over 1 foot, the
Yes, yes. So what's going to happen and what you'll see when we create the tables, if I want you to approximate the area under the curve using, let's say, 4 rectangles, when you create the table, you're actually going to get 5 values. That if you had to create a graph, you'd have 5 points, and that's where that's going to give you this. Does that make sense?
Yeah.
Okay. It's kind of hard when you just have a very generic example. When you guys see the numbers, it'll make a little bit more sense. You typically don't have to draw these, but it's just to give you an idea where these rectangles are coming from and how we're getting these values. Like, I'm not just going to say, oh, we get these rectangles, and you're like, all right, well, how? Where do they come from? All right, so what we have here and what we're using are 1, 2, 3, 4, 5, 6 rectangles to approximate the area under the curve. And we're using the left endpoint. So this is the notation, which you need to know would be L sub 6 is approximately, and then we would have to find the area of each one. So we'd find the area of this, plus the area of this, plus, add it up and approximate the area. We know it's not 100% accurate because look at these gaps here. And then look at these areas are outside the curve. Now, is this always going to be L sub 6? No. Okay, it just depends on how many rectangles we have. So it could be 10, it could be 40, it could be 5, it could be 140, which is just mean. Okay, but you get my point, right? Okay, questions on, this is just, again, very general. I told you there's going to be a lot of explanation before we actually do the math. You guys good? Promise? Okay, so let's take a look here. The whole idea, again, is the same. We have the exact same curve, but instead of using a left endpoint method, we're going to use a right endpoint method. So what that means is we're actually going to go to the right side of the graph. So over here, we started on the left. Here, we're going to start on the right. So we have our A and our B, which are our endpoints. So I can create these verticals that go up to the curve, but now I actually need to create my rectangles. So this one's already created for me, so I'm going to draw over it in green. Here is my right endpoint. So then, again, if I needed to know the width, so let's say again that the width was 1. So here, it's easier if you go from, if I started at 1 and I go 1, 2, 3, 4, 5, 6, 7. Okay, so remember I wanted 6 rectangles. You have 7 points. That's what Ben and I were just talking about. All right, so then I would move back 1. I would find out whatever this point is, and then I would draw my vertical from the x-axis up to the curve and create that point. This is a right endpoint. Again, same thing here, and so on until I get to the end. Now, mathematically, I think it would make sense for me if I started here, had each one of my values, then I had my curve and I could draw up. Does that make sense? Instead of going backwards? But now what I need to do is, using my right endpoints, I need to create my rectangles going to the left. Remember over here we went from the left endpoint to the right. Now we need to move it backwards. So that means I would draw my perpendicular to the height of the rectangle that's before it to create this rectangle here. So when I go to do that from this right endpoint, do I have, I know it's here on your paper, but do I have a green vertical height? So I would have to extend this one until it met this height. Does that make sense? So I have to create a rectangle. And then the same thing here. Here I didn't have to do it. Here I don't have to do it. Here I definitely don't have to do it. But here I do have to extend and create that last one. So this is the right endpoint approximation, okay? And that would be indicated by R sub 6 as approximately. And then we would add up all the areas. Wow. Okay, so this is just basically how the graphs are created. But what this is really going to show us is if I am given a portion of my graph or an interval where the question would be, is the area of this rectangle an under or over approximation of what's going on in that curve? So this is what we need to look for. When we're looking at the accuracy of approximation for left and right sums, We are looking at where the function is increasing and decreasing. Okay, so we need to look at it, and I'm going to show you right here in the table. Okay, we're going to identify either over or under approximation. So let's take a look at a left sum. And when we look at the left sum, so I'm only focusing on this graph, I'm ignoring this one for now, where the function is increasing. So I've got an area here where the function's increasing and here. Would you say this area under the curve is an over or under approximation?
Under.
Why?
Because it's the rectangle is lower than the curve.
Yeah, there's a huge gap, right?
Yeah.
This right here, there's a gap, there's a gap. So the left sum for the increasing portion of the function is an under approximation of the actual area under the curve. Because what I'm saying here is we're missing this part of the area. Because this whole piece right here is the area under the curve. So then where the function is decreasing, look here, the function's decreasing all right here. What do you notice about this portion of the graph? The rectangles do what? They go outside. So it's an over approximation. Does that make sense? Same thing here, decreasing. So here, this is an over approximation. Now, when you're identifying this, you have to write over approximation, not over under, because over under doesn't mean anything. Okay, let's look at the right sum. Increasing function. Take a look where the function is increasing. What can you tell me? Over or under? Over. Okay, and then what about where I'm looking at the right sum decreasing? Decreasing. Under approximation. Okay, so you might get a question given a graph stating it from, let's say, A to B, whatever the numbers are, is the Riemann sum an over or under approximation, and you're going to look at increasing, decreasing for the left sum. If you say, okay, if I'm looking at, let's say, from A to B, and I'm looking at the area right here, you would say this is an under approximation because the function is increasing. You have to give the reason. Does everyone understand? Or you could say f of x is increasing. You can't just say it's an under approximation, period. It's going to say justify your answer. Does everybody understand why this is important? Okay, does anyone have any questions before we move to the next page? Yeah.